MacMaths, let's do some maths today. Okay, guys, I just rambled through my worst video ever on lesson 1 on proof by contradiction. So I'm just going to go through a little bit of support for you for exercise 1A to get you started. I don't really need to go through all the questions with you here. I'm only going to actually go through 2. Might seem a little bit of a cop-out, but I'll explain why it isn't in a second. I'm going to go through question 3 with you and question 8, I think. And there are 10 questions in the exercise. The first few questions just ask you to write these negation statements, so just the opposite statement of, to set up a proof by contradiction, not actually do anything. So question 3 is one where it's the first one that kicks in with a proof by contradiction. So I'll do question 3 for you. Oh yeah, using different colours, aren't I? So I'll use red. I know I'm going to use red last time. I'm going to use green. So actually no, I might not use green because it's not. Yeah, that's okay. I'm going to use green. So question 3 says, the statement is that if n squared is odd, then n is odd. Okay, so that's the statement. If n squared is odd, then n is odd. And basically what we're going to do is prove by contradiction. I'm not going to do that much actually. Prove by contradiction, it's not true. And it says, so there's a part A, it's just leading you into how you do these. Write a negation statement. So the negation statement is that if it's the opposite of this, so we're going to say, assume that if n squared is odd, then n is even. And we're going to prove by contradiction that this is not true, or this is true, whatever. Okay, so here we go. So n squared is odd, then n is odd, and we think that's the case. So we're going to say, well, if n squared is odd, then n is even. So if n is even, we can write it as 2n, and if we square that, we get 4n squared. But this statement is saying that n squared is odd, and this here, of course, we can factorise. It has a factor of 2. So if n is even, then n squared has to be even. So it cannot ever be odd. So we've just proved by contradiction that if n squared is odd, then n is odd, okay, because it can't be even. Okay, we just proved that. Okay, and that's it. That's proof by contradiction. Confusing? Yeah, I think so. The reason that I'm not going through so many of these is because the first few are just writing opposite statements, so you're not really doing any maths. And actually within there, they have, like question 7 is one that goes on, but it's actually proving that root 3 is irrational. And question 9 is proved by contradiction that the cubed root of 2 is irrational. And both of those are exactly the same method as Euclid's proof that root 2 is irrational. So that wipes out half of the questions instantly. And I've gone through the Euclid's proof that root 2 is irrational in my lesson 1. I rambled through that one, didn't I? Didn't do a very good job, but never mind. We'll just brush that one under the carpet. Also, in the textbook as well, in the back, they've got the solutions to these, not just got answers down, but they've got the solutions where they go through it line by line. So you just have to do every one and just flick to the back like I did when I was going through them and just sort of check, okay, that you got them. But I thought I would do, I'd do number 8 for you. I'll do it in red. That use proof by contradiction to prove the statement. There are no integer, how do you spell integer? Oh yeah, integer solutions to the equation. So we're going to prove this one. There are no, I like this one. This one caught my eye straight away. There are no integer solutions to the equation x squared y squared is equal to 2. Okay, so first of all, to prove by contradiction, what we're going to do is we're going to say that there are integer solutions to this. Okay, so there are we're going to say that there are integer solutions, whole number solutions to this for x and y. Okay, so that's our statement. So let's prove that that can't be the case. So if there are integer solutions to this, if you look at this bit here, this is that, you know, that perfect square. It can be factorized, can't it, to x plus y times x minus, oops, hang on, x minus y is equal to 2. Okay, so x, it can be written like that, and if there are integer solutions, then there's only so many, I'm sure this must be the way you do it, there's only so many solutions where you multiply two numbers together to get you 2, isn't there? So it can only be 1 times 2 or 2 times 1. Those are the only two solutions to that. So if that is the case, then x plus y, you know, if I use this one, I don't know why I'm using that one. Let's do the top row. If this is the case, then this is 1 when this is 2, or this is 2 when this is 1. So if this is 1, then x plus y equals 1, and x minus y is equal to 2. That must be the case. So if we solve these, we've got two simultaneous equations, haven't we, here? So let's just line these up. X plus y is equal to 1. Just remember, going back to GCSE, if we add them together, we've got x plus x is 2x, minus y plus y is 0. So 1 add 2 is 3, and straight away you can see that x is 1.5. It's not an integer. You don't need to calculate what y is. I'm going to. I can't help myself. 1.5, so y must be minus a half. Right? So that doesn't work. And if we did it the other way around, we're saying x plus y, the only other option is for x plus y to be equal to 2. Look at here. So x plus y must be equal to 2 when x minus y is equal to 1. And if we solve that, again, adding them up together, we get 2x. I've just done the same thing here. Yeah, it doesn't really matter, does it? 2x is 3, and 3 is the same thing again, isn't it? Okay, so it doesn't actually work. So the only solutions we get to that, for this to happen, is when we've got you know, like fractional, not integers for x and y. Otherwise, it just doesn't work. And so we've proved by contradiction that you can't have integer values in here that would give, you know, for x and y, that gives you two numbers that multiply together to give you 2. Is it essentially that? Okay, because, you know, yeah, because we've proved here that x and y in this here, you know, have to be fractional for it to work. Okay, so there we go. So there's a proof by contradiction. So we said something, it can be equal to that when these are integers, and we've got all of the solutions and none of them are integers. So that's a proof by contradiction. Okay, so I suppose you probably need a little bit of a statement, you know, at the end that says, there you go, you see it doesn't work. All right, have a go at those, do the exercise. You don't really need my support with those because you can just look at the back of the book and it has all of the solutions in. Okay, but they are a little bit bitty, and yeah, it's not like a method I can sort of really show you, or a little quick method, because everyone is different. Okay, I hope that helped anyway. I know it was a little bit rubbish, but doing some proper maths after this, which is partial fractions, I think. Okay, bye bye.